Hello, my name is Kaylynn Chen, and this is my final project for CST1 S89 Introduction to Deep Learning at the Harvard Summer School. The name of my project is Binary Classification Higgs Boson to Tau-Tau Decay. What if our universe was massless? What if the Higgs boson did not exist? How do we observe the Higgs boson? And how do we use machine learning to validate the standard model? These were questions I had going into this project. I wanted to be able to implement machine learning in a way, specifically using deep neural networks in order to classify background from signal events. Signal events are ones that we find very important, such as the Higgs boson to tau-tau decay, and a background event is an event that we have already previously observed, such as the decay of the Z boson into two tau-taus. And essentially, if we are able to answer this question, we can validate the standard model, which is our current best understanding of the fundamental building blocks of our universe. So this is a picture of the Higgs boson discovery in 2012. And this was a revelation because the Higgs boson had been predicted back in the 1950s and was now just being validated in 2012. So as the amount of energy rises, we are looking for a slight disturbance in the smooth curve. And you can see between 120 and 130 giga electron volts, you see that slight little bump that is the Higgs boson. This is a picture of the event of a photon to photon collision. So the data set provided by Kaggle, the data set provided by CERN used in the Kaggle Machine Learning Challenge focuses on these events. And these events are given by 30 features, which are measured by the particle momenta. So the lighter particles, which lighter particles which are decayed into, and the mass of the final particles. So this could include electrons, muons, photons, and tau-taus. This is a picture of the CERN collider. So where we get all of the data from and our primary measurements from in the data set that was used to train the neural networks. So my methodology in approaching this problem was conducting research initially to gain an understanding of the underlying physics. So I wanted to understand which features were redundant and including them would decrease the efficiency of the model training. Also, how do I select for the features which are most important and normalize these features in order for the model to train most efficiently on them? So what does it mean if the particle has a certain jet? What does it mean if a particle has a certain angle to it? And how can I apply this to training and designing the best model? The second step was exploring different types of neural networks. The first one that I explored was a recurrent neural network. I used gated recurrent units because I wanted the data that was passed along to be as efficient as possible. I also explored two fully connected neural networks that were based off of the winning model of the Kaggle machine learning challenge. But I found that without feature generation and CV bagging, my performance was, I still had a high loss function. So I discovered that data preprocessing and mapping, so dropping, log transforming, and finding ways to reduce sampling bias, it helped improve my loss score and my accuracy score. And the fourth step that I took was I tested hyperparameters. So how deep and how wide should I design my model? How should I initialize my weights? And should I set a penalty? So for example, L1 regularization or dropout. So first I plotted the correlation between the features, and I found, expectantly, I found that the derived features were, of course, were very closely correlated to certain primary features. So given by the red, which marks a strong positive correlation. I also discovered that the number of background features greatly outnumbered the number of signal features. This is due to the decay of the Higgs boson being much more rare than the decay of other particles into tau-taus and lighter particles. I also found that certain features given by PRI phi, so primary phi, so that is the azimuthal angle, had constant densities between background and signal events. So these features I discovered would not help the model train its predictions. I explored a recurrent neural network with two gated recurrent units and a recurrent dropout of 0.1 connected to a dense and a dropout layer. And I discovered that the recurrent neural network performed best on having the lowest loss function. I also implemented two different types of fully connected neural networks. These had less trainable parameters than the recurrent neural network, but I discovered that increasing the width and depth of the neural network did not improve metrics anymore. So there was a certain limit that was reached once the number of perceptrons reached 128. In the first version, I implemented dropout, a key normal weight initialization, and I use ReLU for both. So for the second variation, I implemented L1 regularization and dropout, and random normal weight initialization. However, I discovered that L1 regularization did not improve validation accuracy or loss. The first version of the neural network, which used normal weight initialization and ReLU, and was only a moderately deep neural network, so it didn't have as many layers as the second one, actually performed better than the second fully connected neural network. But validation accuracy remained pretty consistent across all scales. I also implemented CV validation in the second neural network, and I didn't find that it improved accuracy very much. But the greatest improvement to model training was data preprocessing. I discovered by using sklearn stratified shuffle split, I was able to balance the number of signal and background events, and the model was able to train better because of that. I also implemented log transformations on the features that had a tail, and when I dropped the redundant features, um, the metrics also improved. I also replaced the measurements that were out of range, which were marked by negative 999 in the data set by 0. What are future implications for in future applications and improvements to the model? So instead of replacing negative 999, if I could gain a greater understanding of the features, I would be able to insert mean data. I would be able to implement data imputation. So that means replacing the out of range measurements by ones that were averages. I could also use CV bagging or feature generation based on the dropped features. However, this project shows that machine learning, specifically different variations of neural networks, can be used to classify events as background and signal with an accuracy of at least 80. This could be further improved by these suggestions, but it also suggests that there is no one way to implement neural networks. One can use both recurrent neural networks and fully connected neural networks, and a hybrid of both in order to improve accuracy. However, it also shows that training on a small data set as this with 255 training instances, a deep neural network is more prone to overfitting, and the accuracy and loss metrics could actually be reduced. Thank you so much for listening to my presentation.